This is the fourth of our videos on 9.3.4, fourth out of six, we're over halfway now, and we're looking at neutralisation in this particular video. And we know from the past that neutralisation is defined as acid plus base goes to salt plus water. But according to Bronsted-Lowry theory, we now have a slightly updated definition of a neutralisation reaction. Neutralisation is a proton transfer reaction, with the acid donating a proton to the base. So yes, acid plus base goes to salt plus water is our old definition. This is our new definition because in some acid-base reactions you don't get water produced necessarily because just the nature of the reaction. An example would be, for example, ammonia plus HCl. In this reaction, the HCl will donate a proton to the ammonia, and that just produces ammonium chloride. So there's no water being produced, but you do have a proton transfer between the acid and the base. And that's how Bronsted-Lowry theory defines a neutralisation reaction. So let's look at some examples. First of all, a strong acid and a strong base example. We've got a hydrochloric acid and sodium hydroxide. You should be able to balance it yourself, so pause the video and have a go, then you can check your answer in a second. Let's see how you went. HCl plus NaOH goes to NaCl plus H2O. That's a fairly typical example of acid plus base goes to salt plus water. But we know a bit more chemistry than that now. We can actually analyse this and look at what's the spectator ions here. So we've got hydrogen ions and chloride ions, sodium ions, hydroxide ions, sodium ions, chloride ions, and water. If you look at this, we've got sodium ions and chloride ions being just spectator ions. They appear on both sides of the equation. So we can remove those spectator ions and we can replace H+, as we know doesn't really exist as H+, with H3O+, and we can write that reaction as H3O+, plus OH-, so the H3O+ from the HCl reacts with the OH- that came out of the sodium hydroxide to produce 2H2O. So basically all this reaction is, when you think about what's really going on, when you remove the spectator ions, all that's really happening is the H3O+, which came from the acid, is just donating a proton to the hydroxide ion which came from the base to turn back to water again. So there's no salt in this situation, there's no acid plus base goes to salt plus water when you look at what's really going on, but you do have a proton transfer from the acid to the base. Next example, reacting sulfuric acid with potassium hydroxide, slightly more challenging to balance than the previous one, so have a go, pause the video, and see how you went in a second. Let's see how you went. You should get H2SO4 aqueous plus 2KOH aqueous goes to K2SO4 potassium sulfate plus 2H2O. But once again, if you look closely, you'll see that, well, the sulfate ions and potassium ions are just spectator ions the whole way through, and we know there's no such thing as just H+ in solution, it's really H3O+. So let's remove those spectator ions again, and we'll see the reaction once again, when you simplify, becomes H3O+, plus OH- goes to 2H2O, and once again, all it is a proton transfer from the hydronium, which came from the acid, and the hydroxide, which came from the base. So these two reactions look very different at the surface. When you first look at the two different reactions, you've got sodium chloride being formed here, you've got different acids and bases here. But when you think about what's actually taking place on the atomic level, the molecular level, all these strong acid, strong base reactions are really just hydronium donating a proton to hydroxide to produce water. So all neutralisation reactions are fundamentally the same reaction between hydronium and hydroxide ions. And there's two big concepts to get right here. That's our new definition of neutralisation, and the concept that all strong acid, strong base reactions are fundamentally the same reaction between hydronium and hydroxide ions, which is this reaction just here. So let's look now at the enthalpy of neutralisation, or don't forget, enthalpy is the amount of heat absorbed, and all neutralisation reactions are exothermic, which means delta H is negative, heat is not being absorbed, heat's being released, and this can be measured by calorimetry, and it's approximately the same value for all neutralisations involving strong acids and strong bases, and that's a value that crops up a fair bit. It's minus 57.3 kilojoules per mole of hydrogen ions, or hydronium ions, and it's the same heat or same enthalpy of neutralisation for all strong acid, strong base reactions. And the reason why all strong acid, strong base reactions have the same enthalpy of neutralisation is because, as we saw on the previous page, all strong acid, strong base reactions are basically the same reaction between hydronium ions and hydroxide ions. Once you take the spectator ions out of the way, because they're not reacting at all, you'll see that all strong acid, strong base reactions are the same reaction, and therefore they all have the same enthalpy change of neutralisation. Weak acids and weak bases, though, have a slightly different enthalpy change, and that's because you've actually got to supply some energy to break the bonds of the non-dissociated molecules, acid molecules and base molecules. Therefore, they've got a slightly lower enthalpy of neutralization because there is some energy involved in breaking the bonds of the non-ionized molecules. But still, that's a very important concept to understand. On the fundamental level, all strong acid, strong base reactions are basically the same reaction, therefore they have the same enthalpy of neutralization. So let's look at some uses of neutralization. We've already looked in the past when we looked at indicators and uses of indicators that we can use indicators to test if waste has been neutralized or not, so that's the same sort of thing. We can use neutralizations in quantitative analysis, such as titrations, which we're going to learn about very soon. You can use neutralization to correct the pH of swimming pools and fish tanks and soil and industrial discharge, and also cleaning up spills. That's what we're going to focus on now, neutralization and cleaning up accidents and spills. And there's two types of spills, but they actually have different treatment techniques. And the first one's a personal spill. And what I mean by personal spill is if you spill acid or base on your skin. And if you do that, you actually never use neutralization to clean up or minimize damage if you spill acid and base on your skin. The reason being is we've just learned that neutralization reactions are exothermic. And if you've spilled some acid or base on your skin, all you're going to do is produce heat, which will add to the burn. In addition, you don't know the exact number of moles of acid or base you've just spilled on your skin, and therefore, if you put acid or base on your skin, you're probably going to add excess rather than less to neutralize the reaction. Then if you had an acid burn on your skin, now all you're going to have is a base burn on your skin instead. So you don't use acids or bases to neutralize spills in your skin. What you do instead, and it's very simple, if you spill acid or base on your skin, you wash it off in cold running water for 15 minutes. And this is particularly talking about strong acid or strong base spills in your skin, things that are quite dangerous, you want to get them off. The reason you wash with cold running water is threefold. First of all, water will wash off the spilt chemical. Most acids and bases are soluble in water, and therefore water will help get them off your skin. In addition, the water will dilute the caustic chemical, changing it from concentrated to dilute, which means it has less effect. And also, water is very good at cooling the burn because water's got a high heat capacity and therefore it can extract large quantities of heat. Hence, you want to use cold water and running water because that's running off your skin. It's taking the heat away with it as it's running off your skin. However, if you've spilled acid or bases in the lab or in an accident, then you can use neutralizations. And neutralizations are an effective strategy for treating caustic or corrosive spills. The neutralization reaction converts the caustic or corrosive chemicals back to relatively harmless water and salt, thus minimizing risk of damage to people, equipment, and the environment. However, chemicals you use for neutralizations must be carefully chosen. First of all, you want to choose a cheap chemical, obviously because you might need to use large volumes to neutralize the spill. It must be non-toxic, because otherwise it would compound the problem. You might have neutralized the acid or base, but now you've poisoned everything in the environment. It must be safe and chemically stable enough to store for long periods of time. And that's so the chemicals can be kept on site, for example, in a lab or in a factory, and they can be kept there for a long time, put away on the side until needed. And you know that when you need them, they're going to be there and they're going to be stable, they're going to be safe. You've got to be able to easily apply it to the spill. That's pretty self-explanatory. It must be effective at neutralizing caustic substances but not be a strong acid or base. You don't want to neutralize things with strong acids or strong bases because if you add an excess when you're trying to neutralize, you just compound the problem. You change it from an acid spill to a base spill instead. You don't want toxic byproducts, so the chemical itself can't be toxic, but also the reactant products can't be toxic either. Preferably it should be amphiprotic. Now, we're going to study amphiprotism very soon. Amphiprotic means it can act as act as a proton donor or a proton acceptor, i.e. act as an acid or a base. And if you've got something amphiprotic, that means you can put it on acid spills and base spills, which is very handy because it's use it in all situations. But you can also use it when you're not sure if the spill itself is an acid or a base, so you can use them in all situations. So the chemicals we commonly use are sodium carbonate. It's a very safe weak base, and that's used for acid spills. And we often use sodium hydrogen carbonate, which is otherwise known as sodium bicarbonate or bicarb soda, because that is actually amphiprotic. The hydrogen carbonate ion is amphiprotic. That can be used for acid and base spills. And that's the end of our fourth video on neutralization.